All right, let's get started. Hello, all. Welcome to another Hoodie LinkedIn Live series. My name is Sudha. I'm a PMC member of the Apache Hoodie project and a software engineer at OneHouse. Apache Hoodie is a lakehouse platform that brings database and data warehouse capabilities to the data lake. If you're exploring Hoodie or interested in knowing more about Hoodie or already using Hoodie and need help, these are different ways to connect with us. We find a lot of users engaging in Slack, asking questions. It's a very robust community helped out by volunteers. We recently announced an AI assistant in the Hoodie Slack that's trained on Hoodie Docs and other resources that can help self start with basic questions. Give it a try and let us know what you think. We hold office hours regularly, 8 a.m. to 8:30 a.m. Pacific on Thursday every week. If you want to connect with us live, um, we can also you can also reach us with GitHub issues and GitHub PRs. While you are there, don't forget to give us a star. Um, for today's session, we have Thomas Chow and Nathan Louie joining us from Notion's data platform team. Thomas focuses on batch processing and data lake ecosystems. He worked on the initial launch of Hoodie within Notion and is currently working on data lake query infrastructure. Nathan focuses on data lake ecosystem and AI infrastructure, especially AI embeddings. In today's talk, Thomas and Nathan are going to discuss how Notion's data infrastructure evolved with scale and how complex workload requirements evolved and how Hoodie has impacted their architecture. This talk will be recorded and uploaded to YouTube Hoodie channel shortly. We will have open floor questions once towards the end of this session. Meanwhile, feel free to send in your comments through the LinkedIn comments section. Without further delay, let me pass it over to Thomas and Nathan to take it forward.
Awesome. Thanks, Sudha. Look, I am sharing my screen, but yes, is the stream focused on that right now or no? Let me see. Can folks see this? Not sure actually. Okay. Okay. I will get started. Please let me know in the comments if you can't see this. But thanks everybody for joining. My name is Thomas. Like Sudha mentioned, I'm an engineer on the data platform team at Notion. And I have Nathan with me, my colleague, and together we'll walk you through Notion's kind of journey through different stages of scale and where we are today, basically, versus where we were 3 years ago. The first thing I want to talk about a little bit is just Notion's data model in general. It's actually quite a complex data model, and it poses its own challenges during scale. So, as you all know, kind of Notion is a collaborative documents product. We are very similar to things like Google Docs, and Coda, things like that. And the way we model document sharing is through the concept of a block. So here's an example of a page in Notion and lots of content on it. Each one of these things is its own block. So you can see images, text, headings, toggle lists, tables, collections, and stuff like that. So all of these things are actually modeled on the back end as the same entity, even though they visually appear very different. There's a lot of different pieces of metadata that's associated with each of these blocks. There's different block types. Image, you can see that here. And the way they behave, the way they're rendered in the UI is actually very different. But on the back end, they're all modeled with the same structure and schema, basically. So it's actually it's highly configurable on the front end. But on the back end, actually, we kind of fit all of this metadata into the same structure. So I'll talk about why that matters a little bit. But first, to give you a sense of the data scale, the doubling rate that we experience, just 1 second. Okay. The doubling rate that we experience actually at Notion is about 6 months to a year. So in 2021 start, we had about 20 billion of these block rows that you see. So in production, every single piece of content that any one user authors in a single workspace consists of a block row, creates a block row or updates a block row, and we have 20 billion of those at 2021 start, and 70 billion around 22 end. And today we have 200 billion block rows and counting, right? So between sort of just over a year, basically, we saw triple the amount of growth in terms of block volume. So kind of our doubling rate is very quite aggressive here with our largest data set. The file size at rest right now is about has grown to be about 50 terabytes compressed. That's exactly one snapshot, one version of the block data. And now obviously we have a bunch of derivations and a bunch of sort of different versions of that data. So the aggregate volume is a lot larger that we're talking about, like hundreds of terabytes. I'll just talk a little bit about the timeline, a little bit about how our infrastructure has evolved to accommodate this data scale. Before 2020 was actually quite simple, right? So many startups go through this phase of single Postgres instance. Everything on the app runs against this single Postgres, and whatever analytics you have at the time also works off of this single Postgres instance. And for us, we recently outgrew that pretty quickly. And by the end of H2 2020, we had like a Postgres sharding event, basically. So this is actually a blog that you could see online, but basically we turned our single Postgres instance into 15 logical shards and 32 actual physical database instances. So you can kind of see here where each table how each table is kind of laid out after the resharding. So this kind of gave us a total of 480 distinct shards of our Postgres instance. Which is pretty fundamental architecture change that actually is very pervasive throughout our offline infrastructure as well. Fast forward to 2021, we actually brought up a formal data warehouse architecture. So it's fully productionized and everything, where we were doing analytics and reporting. This is kind of like the stack that we use to Postgres. Ingest via Fivetran into Snowflake, so fairly modern. And then we kind of use Snowflake as our data warehouse to power analytics reporting and a bit of machine learning at the time. Obviously, there were some challenges with this as time went on, as our product grew. The way that again, like I mentioned before, Postgres at this point is sharded 480 ways, right? So in Fivetran, that actually the sharding scheme follows basically. So we have set up a Postgres connection for each instance, and we conduct kind of like full incremental syncs actually on an hourly basis into ultimately the destination is Snowflake. And then we kind of stitch together shards of Postgres to form the block table and all the other tables that we have in production. And so this architecture worked well for a little bit, but our block table actually was the most difficult to deal with because it was sort of the largest and fastest growing by volume. And we started to see problems with Fivetran that we couldn't really resolve on our side by ourselves. The per hour incremental syncs obviously started to fail. A lot of ooming, actually, a lot of issues, latent sort of issues handling bursts of volume, because hourly syncs actually, it's actually quite variable in terms of the volume that you observe in the application. And so Fivetran was sort of connected to our Postgres via the Postgres replication slots and listening to the wall, actually. So we had the wall set up, and Fivetran was sort of just tailing the wall and listening to updates there. And so bursts in the wall, obviously, Fivetran had a little bit of trouble dealing with, and more importantly, I think we couldn't actually do anything to handle variation in like block update volume, right? So it's Fivetran is kind of like a third-party product, and there's few knobs that we can actually tune. And so we furthermore actually downstream, the load into Snowflake was also challenging to deal with, mostly because of cost, actually, because loads into Snowflake actually took quite a long time. Sometimes it actually bleeds over the sort of like the hour SLA that we have, but also it's very expensive to actually load something like like several tens or hundreds of terabytes into Snowflake in aggregate day over day, right? And so we took a look at this. Basically, the type of update pattern that we see actually is that incrementally there's about 1% of our 1% of our blocks get upsert day over day, kind of thing, right? And 90% of those upserts are actually updates. So our write volume is actually update heavy rather than insert heavy. But in aggregate, like the total upsert volume is actually quite small relative to the existing table size. So we wanted to kind of turn to a different, like obviously modernize and turn to a data lake architecture to support this type of write volume. And obviously, so we obviously settled with Hoodie. But I'll talk about why we picked Hoodie. Because at the time, we had a couple options, right? Hoodie, there's Iceberg, and there's presumably also Databricks as well. But at the time, basically, these were the advantages that we saw in Hoodie. First of all, there's Hoodie's good at incremental processing. At the time, I think Hoodie was actually leading in terms of those capabilities. They started with the incremental processing problem first with the technology. And more importantly, I think Hoodie gave us the ability to do random upserts pretty efficiently. And that's core to Notion's product, because a lot of the block edits basically are not correlated with recency or anything time related. It's just random upserts to different blocks based off of users' edits, basically, right? So that was attractive to us from the start. The second thing is actually Hoodie actually has pretty good integration with Postgres. There's out-of-the-box CDC, basically, the Debezium connector that we could just simply deploy. So what we did was, eventually we essentially just deployed Debezium on an EKS cluster and had that listening to the Postgres replication slots, the wall through Postgres replication slots, which we already set up already for Fivetran, right? So a lot of our existing infrastructure was already configured for that. We already knew how to do that, and Debezium was already sort of provided to us. So that was good. The third thing is that Hoodie has really good indexing, actually. So we actually ended up settling on the Bloom filter index for writes, just because we had, our upsert pattern is fairly random. And so at the time, Bloom filter index was the best one for that. It was good enough for us, at least. And so, yeah, that was good. Obviously, Hoodie has directory level partitioning. So that actually lends well to our sharded Postgres architecture, and I'll sort of talk about that a little bit more detail later. But finally, actually, this one's a little less obvious. We saw actually really good open source velocity, and we already had relationships set up basically internally with OneHouse. So early members of our data platform team actually, worked closely with the OneHouse team. And we thought that was invaluable for us being able to get up our data lake architecture in a fairly short amount of time. Actually, it was just about a quarter or two, basically, where we were able to spin up this new architecture. So yeah, that's ultimately why we settled on Hoodie. I would say our open source relationships with OneHouse was actually really essential to the success of this of bringing this technology to Notion. And the ability to kind of just not have to engineer, reinvent the wheel for a lot of these components was really valuable. So I'll talk about sort of what our data lake architecture looks like today. So since 2022, this is our new architecture. We kind of ingest data from Postgres, obviously through Debezium CDC, pipe to Kafka. Then we have sort of batch incremental updates happening against our Hoodie data sets. And then sort of downstream Spark pipelines kind of do that ETL for us. And so just to clarify, I guess this architecture is there for our largest data sets, but our Fivetran Snowflake setup is also still exists today for a majority of the smaller data sets. And in particular, it still exists for third-party data sources, not just Postgres, right? So we actually have both of these architectures set up. And just to be clear, downstream of Hoodie, we actually still have Snowflake for derivations of our block data. This is kind of our steady state incremental processing setup. We use Hoodie Delta Streamer, which also is out of the box, basically. This is sort of, we've configured it to kind of do copy on write pattern. And there are some, okay, so there are some details here that we've kind of like design decisions that we made here that help us kind of scale. So the first thing that you see basically here is the sharding layout. On S3, we have high style partitioning basically. So our block table is sharded 480 ways in our online store. And so we kind of mirrored that sharding scheme downstream because it's a very natural sort of like partitioning scheme. Everything, it's uniformly distributed by volume by definition from the online world. And it lends itself well to kind of different partition push downstream optimizations downstream. So we decided to do that, go with like the Postgres shard as our partition path. We have a source ordering field. We basically chose to update sort our data based off of when the block was last updated, which is the event LSN here, effectively the event LSN here. That gave us some loose correlation between block upserts. So it helped us kind of control a bit of the write amplification problem a little bit. It didn't solve it for us entirely, but it did improve things to the point where it was acceptable for us. So that's kind of like the detail there. And obviously like Delta Stream, we have table level topics in Kafka that, like represent the wall changes for a particular table. Delta Streamer is kind of sort of listening to changes on Kafka and applying those compacting those updates and applying them to our Hoodie data set. Some of the things that we kind of went through when setting this up was obviously the write amplification problem. So we spent a good amount of time tuning file sizes for that and settled around 300 megabytes compressed per K as kind of like an acceptable range and performance for our writes. Obviously, like I mentioned, sort key was on last updated time. So kind of the posit here was that like blocks that have been Notion blocks that have been recently updated. The Notion blocks that experienced the most active updates were the ones that were most recently updated. So we were trying to cluster kind of like the majority of the upsert activity to the fewest set of blocks, the most recently updated set of blocks. In practice, this isn't entirely true because a lot of blocks, we do actually see some randomness, some uniformity distributed, update uniformity distributed across old blocks and new blocks. But in general, this helped us control the write amplification even more a little bit. Again, consistent sharding scheme, borrowing the sharding from Postgres as well. So actually our improvements here, basically, we saw a pretty good net saving, about 1.25 million a year. So basically getting our largest data sets off of the 5-tran ingest and into Snowflake onto Hoodie actually allowed us to have some monetary savings. It actually improved 5-tran performance overall for us. So other tables weren't so, like heavily affected. If we needed to conduct full resyncs, that wouldn't take, multiple days. That would just take a couple hours. Historical 5-tran resync also could be done on a regular basis. So we actually now have, like history tables, 5-tran history tables for a lot of other data sets. And today our Delta Streamer is configured to run syncs every 4 hours. That's kind of like the level of freshness that's really beneficial for us. We could obviously actually go even more incremental, but for now, basically, this 4 hours is kind of acceptable for all of our product use cases. Okay, so that's pretty much the data lake infrastructure as it is today. I will turn it over to Nathan to kind of spotlight one of the more recent significant products that we have at Notion and have him kind of talk about how the data lake enables that.
Cool. Thanks, Thomas. Hey, I'm Nathan, engineer at Notion, is Thomas. Yeah, today I can spotlight the Notion AI Q&A product, and specifically how did the setup that Thomas described that we've invested in enable us to build on top of and launch such a data heavy product. Next slide. Cool. So first, to give some context on what we had launched back in November, Notion AI Q&A, you have your workspace data in documents and databases, and essentially you can pull up a chat window to ask questions about your organization's data and get summarized responses with citations referring back to the source of truth documents. I encourage everyone to try it out. It's really cool. Next slide. So on the data team, what is our objective in how we support this product? Essentially, in order to have these references to the source of truth documents and have the large language models refer to your data, you need to use a vector DB and store your data in such a fashion such that it can be found at query time. And in order to do that, we need to run these very large jobs to load the data and continuously update the data to the vector DB. I'll describe two paths here, the offline path and the online path. The offline path is done once per workspace to bootstrap the data in the vector DB. And this is done through large batch jobs. So as you can see, the block data to data lake part of this diagram is a very simplified version of what Thomas described. And from there, we have a foundation to generate the embeddings for workspaces. And workspaces can vary in size quite a bit, and some can be very large. Sorry, this is meant to be online and offline. Anyways, the online path described up top has incremental updates through Kafka, in which we process new page edits and send them to the vector DB at the point of at the time they were written. Next slide. Cool. So how does Hoodie help us with such a objective? And ultimately, I think Hoodie serves as a good foundational data lake to build an AI product on top of, because we have the flexibility to define these large, flexible processing jobs, using the Hoodie format that we wouldn't have been able to as easily do with our previous setup with Fivetran and Snowflake. And the 4-hour update cadence that we had defined over the journey on the data lake really served us well here, because once we ran through the offline batch jobs, the online catch-up period was at least within a day, and enabled us technically to even get this project up. These jobs, these offline jobs, are pretty large, with 100 million plus vectors per batch that we're looking to scale up even further. And yeah, we can continuously deliver value to our customers and keep this product functioning. So yeah, that's the spotlight on how the data lake has helped launch the AI product.
Cool. Thanks, Nathan. Yeah, so I think that's it for the presentation portion. Just want to give one last thanks basically to the One House team. Like I said before, they've been pretty invaluable in helping support us, giving us advice on data lake architecture throughout this whole journey. So thanks to the One House team, Vinod, Alexi, Ethan, Suda, and Kyle, to name a few. I think that, we can open it up for questions now.
All right. Maybe I can go through some of the questions in the chat here. I think one is already answered. Somal had a question on whether that's elastic or pinecone. Looks like pinecone for your vector embeddings. And I think, Vinod had a question on your slide for online and offline processing. He asked, is it like a Lambda architecture? Maybe we can you help understand that?
Yeah, it's Lambda-esque, basically. Yeah, so we have real-time updates happening from the application to being piped into Kafka, and then the same code kind of we kind of reuse the same code. We don't actually reuse the same code. So currently, because our application is written in TypeScript and most of our Spark jobs are written in Python, so we do have to replicate the logic online and offline. But for the most part, yeah, that is actually currently like a pain point that we're actually looking into. So trying to see if we can. I think the challenge there is basically really the difference, the programming language, and a lot of our sort of engineers are either well versed in TypeScript or versed in Python. So it's a bit of a challenge there. Yeah.
Got it. Makes sense. I think we don't have other questions here. I think there is one comment on RLI index for much faster upserts for massive data set.
Yeah.
I think,
right.
Yeah, please go ahead.
We are actually, I think RLI came later. So actually we should probably try to experiment with that actually. So that's a good point. And it probably benefited from our right workload in particular. So
Got it.
There's a couple other questions. I think there's a question around ingestion throughput.
Yeah.
Per minute, basically. So min-max, Snowflake and Apache. Yeah. So let me think. I don't actually have, let's see, the exact numbers, but I can tell you sort of in aggregate what we generally see with Snowflake. So we're able to sort of we're able to sort of load 200 billion rows within 2 hours into Snowflake, that maxing out parallelism. And Hoodie, our incremental steady state is kind of roughly maybe several hundred million records per hour, basically. That gives you, if that gives you a good sense. But I think actually now, but I think it's sort of using different resources on the cluster, a different amount of resources on the cluster. So it's not quite an apples to apples, but I'm certain we can actually get equal or better throughput with Hoodie for like a fraction of the price, because Snowflake is actually quite expensive to reach that type of throughput. It's about like, it does cost us thousands of dollars to reach that throughput. Whereas for Hoodie, it's a fraction of the price, really. So.
Got it. I think we are on time. There are a couple more questions, but I guess we should be able to get to them offline. But great talk. Thanks so much, Thomas and Nathan, for taking time and sharing your journey with the Hoodie community. There are more events coming up in the next weeks and in the first quarter of 2024. Please have an eye for the events on the LinkedIn Hoodie page. And thanks all for joining today.
Great. Thanks, everybody.
Thanks, everyone.